We've been looking a lot at equations, so let's think about inequalities. Inequalities are sort of the other kind of relationship that variables might have. So what do solutions for inequalities look like? In general, solutions to an inequality will have there will be lots and lots of solutions to an inequality. So the problem isn't really finding a solution. The problem is making sure that you find all of the solutions. And there are infinitely many of them generally, and so we won't be able to just list the solutions. We'll have to draw a picture of the solutions in the xy plane. And I say the xy plane because all of our examples will have two variables, and so we'll only need an x-axis and a y-axis to describe all of the possible solutions. So how can we get a picture of all of the possible solutions? Well, let's take this as our example: y less than or equal to x squared. Now, as long as this x squared part is big enough, we will have a solution. So, any point over here on the positive x-axis is going to be a solution because y is 0 here, right? So all of these points will be solutions. Over here we'll have solutions too, and all the way in here. You can see there are so many of them that it's not really practical to find solutions one by one. We have to have some sort of bigger picture thinking in mind to make sure that we get all of the solutions. Well, the thing to realize with inequalities is if we replace this inequality symbol with an equals, right, we can graph this curve, y equals x squared, and that's a parabola that we're familiar with, right? It's going to look like this, I guess. Okay, so that's this parabola. And the reason that it's a good idea to draw this parabola where y is equal to x squared is because since this is where y is equal to x squared, this curve will separate places where y is less than x squared and where y is bigger than x squared. So, we kind of expect that one side of this curve will be full of solutions and the other side will not be solutions. We just need to figure out which is which. To figure out which is right, the only way that if we start, okay, let's plug in a point. So to see if there are solutions below this parabola, let's just plug in any old point below this parabola and see if it's a solution or not. So this is the point 5, 4. To see if this is a solution, we can just plug it into this inequality and see if it works. So y is 4. We want to know, is that less than or equal to 5 squared? And yes, it is. So this point is a solution. Now imagine if you're at this point and you start moving this point around the plane. X squared at this location will change and y will change, but as long as you don't move too far away from this point, x squared will still be greater than or equal to y squared. How is it that x squared could end up less than or equal to y squared? Well, for x squared to end up less than or equal to y squared, at some point we're going to have to cross the boundary where x squared is equal to y squared. But we've drawn the boundary where x squared is equal to y squared. So the only way we could, by moving around this point, the only way we could arrive at a point that is not a solution is by crossing this boundary line. Well, that means every point on this side of the parabola, right, we can reach all of these points without crossing the boundary line, the boundary curve. And that means that all of these points are solutions. So all of these points here are solutions. Above the parabola here, these points, well, it seems plausible that they won't be solutions, but just to make sure, we could check a single point. So maybe let's check 0, 5. So if we plug 0, 5 into this inequality, we get 5 less than or equal to 0 squared, and that's false. So this point at 0, 5 is not a solution, and that means that all the points above the parabola are not solutions. So you see what's happening here is this boundary curve that we get by replacing the inequality with an equals is sort of separating the plane up into some regions, and then we can just check each region separately just by picking some point in that region and plugging it in to see if it works. Maybe the last thing we need to do is figure out, so we know stuff above the parabola is not a solution. We know points below the parabola are solutions. What about points on the parabola? Well, remember, the parabola is where y is equal to x squared. If y is equal to x squared, is that a solution to this inequality? Well, for this example, yes, because this inequality says or equal to. So if y is equal to x squared, we have a solution. And that means that this boundary itself, this boundary parabola itself, is composed of solutions to the inequality. To indicate that they're solutions, we will use a solid curve for this parabola. If our boundary curve isn't a solution, then we'll use a dotted boundary curve like this to indicate that it's not made up of solutions. So this trick that we figured out for this particular example actually works in general for graphing solutions to an inequality. So in general, if you have an inequality, what we'll do to sketch the collection of solutions is replace the inequality with an equals and graph the resulting equation, whatever it turns out to be. The resulting curve will split the xy plane up into some regions, maybe 2, maybe 3, who knows. But for each region, we will test if that region satisfies the inequality just by plugging some test point in to the inequality, some test point that we've chosen from that region. So we'll do that for each region that the curve cuts out of the plane. And then we'll know which of those regions is composed of solutions. Then also we'll have to indicate if the boundary curve satisfies the inequality. So we might have to replace the boundary curve with a dotted boundary curve if the boundary curve doesn't satisfy the inequality. So let's look at one more example. Now let's sketch the collection of solutions to this inequality. So first we need to replace the inequality with an equals, so x squared over 9 minus y squared over 16 equals 1. And then we need to graph this. Well, this is a hyperbola. Because the minus sign is on the y squared, this hyperbola is going to open left and right, and it looks like, so we've been calling this value a. Looks like a is 3 and b is 4. And also it hasn't been shifted from the origin, so this is still centered at the origin. So we can go left and right 3, up and down 4, right, and this gives us this sort of guide box. So these dotted lines are just the guide box for our hyperbola. These are not, this has nothing to do with the inequality. So our asymptotes for the hyperbola are going to look like this. Okay, so the hyperbola itself, so our vertices are on the transverse axis, which is the x-axis. So our hyperbola looks like this. Okay, now you can see we have 3 regions. There's this one over on the left, there's the one in the middle, and then there's the region on the far right. So we need to choose a point from each region and check if it satisfies the inequality. So let's choose maybe -6, 0. Let's choose 0, 0. And let's choose, how about +6, 0. Okay, so for -6, 0, remember I'm going to be plugging these points into the original inequality over here. So for -6, 0, I get -6 squared. Careful with the parentheses, right? This minus sign belongs inside of the squaring. Over 9 minus 0 squared over 16 greater than 1. So this is going to be 36 over 9. Is that greater than 1? Yes, clearly. So the far left region is full of solutions. I'm going to draw the solutions using this red pen just so that all the black drawing that I did on the graph so far doesn't confuse us. Okay. For 0, 0, when we plug that in, we get 0 minus 0 greater than 1. Is that true? No, that's false. So the region in the middle is not full of solutions, right? All of the points in this middle region are not solutions to the inequality. And then for this far right point, we get 36 over 9 greater than 1, and that's true. So this right-hand region is also full of solutions. Okay, now we have to decide, is the hyperbola itself composed of solutions to this inequality? Well, the hyperbola is where this expression is equal to 1, but for the inequality, we want that expression to be bigger than 1. So on the hyperbola, it's not bigger than 1, it's equal to 1. So the points on the hyperbola do not satisfy this inequality. So we have to draw this hyperbola with a dotted boundary like this. Okay, and then maybe let me erase the original hyperbola just to sort of clean things up a little bit. So the red points here are solutions to this inequality, not including the boundary hyperbola. Okay, so because a single inequality can split the plane up into more than 2 regions, you really do need to check each region individually to see if it's a solution, if it's composed of solutions to the inequality or not. What it's not really fair to do is, if you have some curve that splits up the plane, it's not really fair to just check one side, use a test point on one side, and if that side of the curve is full of solutions, it's not fair to assume that the other side doesn't have solutions. So there are 2 reasons for that. One reason is this example. What if you have 3 regions? How do you know which ones are solutions? But also, it's possible that both sides could be solutions.